Models and testing. Patrick Michel will be continuing to host that session. Before we continue session 4, however, we also have some announcements from Makoto.
Thank you. Good morning. From LOC, there are 2 announcements. One is a group photo. So today, before lunch, after morning session, before lunch, we will take the group photo in this room. So please stay here. So this is one announcement. And the other one is, this is a last announcement for the bus tour on May 20. If you want to join this tour, please tell to LOC just today. Okay. Okay, that's all from LOC.
Okay, so good morning, everybody. So we are starting the last part of the session 4 about deflection disruption models and testing. So the first talk will be by Angela Stickle. She's a senior scientist at APL, and she's an expert in shooting into rocks, but modeling, of course, and only, hopefully. And she will present impact simulations in support of the double asteroid redirection test and the asteroid impact and deflection assessment, AIDA. Thank you, Angela.
Brent's got the timer, okay. And then I just okay. Good morning. You guys hear me? If I stand here? Okay. So I am one of the leads for the impact simulation working group for the DART and AIDA missions. And so I'm going to talk to you today about some of the work we've been doing in support of those mission concepts. It's just going to be sort of a highlight reel of some of the things that we've been going on. And so there's a wide group of people working on impact simulations for DART and AIDA. And the people listed here are some of the ones whose work we're going to be featuring today. To start out with a little background, so we know we've had 2 planetary impact scale missions and tests to date, the Deep Impact mission to Comet Tempel 1 and the L-Cross mission to the Moon. And these are really valuable in teaching us about impact processes at large scales on planets and planetary bodies. We can learn a lot from small-scale experiments, but there's always a question of how do you scale that up? And that's an issue that we have, as all of you probably are aware of, with planetary defense and kinetic impactor missions, in that we can do a lot of small-scale tests, but we don't really know what that means for a large-scale kinetic impactor if we should ever have to do one. So doing these large-scale experiments is really important. We can sort of constrain one half of the problem really, really well. We know the spacecraft, we know its materials, we know its density, we know its trajectory, and so then the things that we measure can tell us a lot about the process and also about the target. However, doing these things also requires that up front we sort of make some estimates about the target so that we can design a mission correctly. And so in order to do that, we have been doing a lot of modeling to try to tell us what's going on, and you heard some of that yesterday. And so the DART mission is going to be our first direct test of this. So can we predict what we're going to see in a kinetic impact deflection based on some of the things that we are estimating up front? So as you might imagine, as part of that, simulations play quite a large role in our mission planning and mission understanding of what's going to happen. And so we have a team of people that's working on a wide range of models in support of this. And basically, we are supporting this here. This is one of the DART mission goals and requirements, and this is directly what we're supporting, is that we're going to be validating predictions of deflection, don't lean on this, by hypervelocity impact. And so to do this, we have a few different activities going on. One of them is a benchmarking campaign to benchmark the impact codes against each other so that we can better understand predictions that are provided by different people. And then we're also going to be exploring some of the parameter space that Diddy Moon might fall into to better understand what we might expect to see from DART. So starting off, benchmarking activities. So in 2000, 2008, Betty Perazzo performed a benchmarking study for many of the main hydrocodes against each other, looking at strengthless targets. So we didn't include any strength models in these, and the codes were validated against each other, and they did really well, as you might expect and hope, that the codes sort of varied within about 10 to 20% of each other, depending upon the condition. However, because of the size of Diddy Moon and the sort of regime of impacts that we're in for something like DART, we're going to be in what's called the strength regime. And that means that the material strength and material properties are going to be really important to understand the cratering process and the ejecta formation that causes the push. So we wanted to understand then, how do these codes do against each other when you add strength into the problem? And what might that mean for predictions from different codes that have different strength models or different material properties implemented in different ways? So we have about 6 or 7 groups of people working on this, depending on the day. But, and we were looking at a set of cases with very specific conditions to look at the strength models that are implemented. And this has not previously been done, and so it's going to be, I think, a good leave behind of the DART and AIDA mission studies at the end, so that we can understand how these codes perform with respect to each other. So doing these sorts of simulations can tell us a lot of things. We can kind of pull out sort of, not unlimited, but pretty much whatever we want from the codes. So this is an example of some information we've gotten from some of our European colleagues in the UK. And this is showing various things that they're looking at as a function of resolution of the simulation. And so you can see we can get crater size, so depth and diameter. We can get the beta factor, so how much momentum we are transferring to the body. And then various things about the ejecta, which are important if you're going to have some sort of either follow-on spacecraft or accompanying spacecraft to understand where the ejecta is going to be so it doesn't get sandblasted. And so you can see, as we might expect, these things are varying as a function of resolution. So we're going to have to understand how resolved we can make these codes. And we can pull out all of these different things. So these are the sorts of things that we're wanting to understand for the DART mission. One of the big ones that we talk about is the beta factor, which most of you are, I think, aware of or have heard or know. If not, it's basically just the momentum you get from smashing a kinetic impactor into a body. So what happens is you hit the body, you get ejecta out the backside, and as long as you don't hit it too hard to either disrupt it or spall things off the far side, you get a bunch of ejecta that acts sort of like a thruster and pushes the body and enhances its momentum to deflect it. If you have no ejecta, you just get a beta of 1, which is just the spacecraft's momentum added to the body. But if you have any other ejecta coming off the impact side here, you get an increase in momentum. So this is the main parameter that we are pulling out of these models. When we do this, there's always a little bit of a question of how do you calculate beta and how valid is the calculation based on the simulation. And so what we've done is in order to ensure that we can do this across different code styles, is we've calculated for a case of an impact into a 30 centimeter sphere, beta in sort of 3 different methods to try to understand if any of them provides sort of an answer that we wouldn't trust. So the first thing that we did is we embedded a bunch of tracers in the middle of the target and summed all of the momentum after impact. And that gives us a beta of about 7.8. We also put a tracer in the top to measure the ejecta momentum, and if you sum all the momentum there, you get almost exactly the same. And then we put a tracer in every single grid cell of the model and measured the ejecta moving through and summed up all of the momentum there. And we get within about 10% again of the momentum. So we're pretty confident that amongst the codes we'll be able to calculate beta in a variety of different ways that's sort of well suited for each code, and it'll give us the same sort of answer. Okay, so now stepping through some of the benchmarking results. These next couple of charts are just going to show a few comparisons between the different codes. And what we're seeing is that for comparable cases between the codes, we see, similar to what Betty Perazzo saw, variations of about the 10-ish% between the codes. So if you have sort of a weak rock that you hit into, calculations done using the CTH code give you about 11.6. If you converge to a value of 11.6 for beta, using Spheral, which is the code that was talked about by Megan yesterday, you get a value of 12. And so we're pretty close when we start adding in sort of weak strengths. Again, in the strengthless cases, like was seen by Betty, we see sort of a variation around 12, and these different sorts of codes are converging to those values, which is really encouraging. When you add in sort of a higher strength value, something that might be more appropriate to an asteroid, you see a little bit, maybe a little bit more variability. This is from ISAIL and this is from Spheral, but again, it's sort of in the 10 to 20% range. So we're pretty confident that these codes, even when you add in strength models that might be implemented a little bit differently, are going to give us sort of consistent results across the models. The other thing that we're doing is, like I said, so that's sort of the benchmarking bit. And the other thing that the working group has been working on is trying to understand what might actually happen when we hit Diddy Moon. Excuse me. So as I said, there's a lot of things we know about an experiment like this. So we know roughly the diameter of the target. We think it's an S-type asteroid. We know the separation distance in the system, so the dynamics. We know the impactor parameters really, really well. There's a lot of things we don't know, though, and so these are things that we have to model to try to better understand what might happen. So there's a couple of ways you can do this. You can do what people sort of traditionally do, is you pick a parameter, and then you kind of dance around it along the space, and you get sort of this n-dimensional space and kind of work through different combinations of things. This can be really computationally expensive. You sort of have on the order of, 2n, what is it? I don't remember the actual equation right now, but it requires a lot of runs. It's very computationally and time expensive. So we do a little bit of this. We look at n members, but we don't really want to do this for our whole n-dimensional parameter space. We're in the sort of 10 or 11 parameter range. The other way that you can do it, and Emma Rainey has a poster on this in the other room, so talk to Emma, who's sitting in the back over there somewhere, if you have questions. She's got some really cool results, is that you can do what's called design of experiments, which is statistical representation of the sort of response surface. And it allows you to fill in this space in a much more efficient manner and to learn what parameters are actually statistically important in changing something like beta. So we've set up a suite of sort of a screening experiment to see what sorts of things are statistically important in varying beta, and so you find that it's really just 2 or 3 parameters that will really be important in judging what beta might be. So this is something that we're really excited about to sort of limit the number of runs that we have to do. Within that, I'm going to just run through a couple of things that we're doing to give you an idea. I think we heard yesterday that porosity is one, and Emma's study has also shown that porosity is one of the more important parameters that will affect beta and the cratering process in an asteroid. And so we know that it will affect the crater shape and the ejecta. So you see here is a set of simulations from 0 porosity up to 60 porosity, and you can see that the crater shape becomes very different and the ejecta becomes very different. Megan Brooks-Sial did some simulations using Spheral, and then Paul mentioned these yesterday, that you see as you increase porosity, beta decreases as you might expect, but the delta V actually increases by quite a lot, so you're getting this increased push due to the less mass. Another thing that we're looking at is looking at the internal structure and what type of porosity might be present. So there's a lot of discussion of how something like Diddy Moon might have formed and whether or not it's a rubble pile. So we have been doing some simulations to try to examine if this will affect the problem. So you can see here is a setup of a rubble pile asteroid that's sort of meant to be a simulated Diddy Moon, and we're hitting it at 6 kilometers per second, which is what the impact velocity will be for DART. There's lots of things going on. And so this is what it looks like. You hit in the body, and this is the pressure wave going through. You can see you get a lot of smushed boulders and things like that. You get sort of discontinuous pressure between the bodies as it kind of jumps from boulder to boulder. And what that does to the beta and the delta V is actually, the beta changes by a little bit compared to sort of a coherent case or a porous case, but the delta V changes by a lot again, so this can have a large effect on the process. So we're examining this right now in more detail. And I think that's it. So I will take any questions. It's hard to see you guys.
Good morning, Angela. That's wonderful work. It's really exciting. Am I remembering correctly, though, that you're also validating the various hydrocodes against laboratory impact experiments for baseline comparisons?
Yes, so we are planning to do that. We have one that we have sort of sent out so far to compare against, and so we plan to do that as well. It might be on a separate paper, but yes, because I think that's really important in order to really understand if they're telling us what, like, true things.
Right. It's good to see the consistency, though, with the beta so far. So
Yeah,
that's
thank
great.
you.
Okay, other questions? Okay.
It seems to me one thing that's really important that you ought to report on is not mean beta, but spread in beta, because the uncertainty in what you can achieve when you hit something is probably just as important as achieving a mean delta V.
Do you mean in each model or for like a type between the codes? Or
Well, so imagine some 2017 PDCs coming in, and you don't know what it's comprised of, and you don't know a whole bunch of stuff. It seems to me you can have lots of experiments and so forth, but until you actually hit it, you won't know what the effect is. And so
Sure,
therefore,
yeah.
understanding the uncertainties as well as sort of the means is really important. Because
Okay,
if you can say, for example, within the margins, for sure you will achieve a delta V of such and so, you're a lot more secure than just saying the mean delta V should be 2 centimeters per second or whatever.
yeah, that's a good point. And I agree that's something we try to do when we get to the end members, sort of what the minimum, maximum beta we might expect are. And I can say from the simulations we've done so far, there's sort of a wide range. We're in sort of the 1.5 to 4, depending on the material properties chosen. But yeah, that's a good point.
Okay,
Good, Andy.
thank you, Angela.
Thank you.
Okay, so we move to the next talk. Will be by Gonzalo Tancredi, who was the main organizer of the Asteroid Comet Meteor meeting, which was apparently very nice. I missed it, in Uruguay, so congratulations. And the talk will be laboratory and numerical experiments of impact-generated waves in agglomerated asteroids. It's this one. It's a separate directory. Okay.
Yeah, but it's under session 4.
So it should be there.
No,
Tane, standoff.
no.
Ah, so it's not in the right one. Okay, let's go for it.
4? Yeah, we put it in session 4.
No, it's not. Maybe session 3, yeah. No, session 4.
Session 5? No, I'm
Try
sure that
file,
it-
yeah.
No, it's in a separate directory. Why? I put it today in the morning. No?
You have a USB?
By the way, your talk is, there is Tancredi in the file, the name file.
PDC 2017 Tancredi.
You should look
Tancredi.
for Tancredi. Sorry.
I put it today in the morning. No?
So it's not.
Okay, so maybe
Yeah.
we exchange it.
I have it in the
Ah, okay. So, disruption.
should be PDC 2017. This one, that one. Yep.
So maybe I just put it here. Okay, sorry for this. can take this.
This one, and then with a
Yeah.
arrow. Okay, well, thank you, Michel. I'm happy to see several faces that we saw a few weeks ago at the ACM, but now in the antipodes. I will talk about what we have been doing with some colleagues of the physics department and the computer science departments about numerical and laboratory experiments of agglomerated asteroids. And I just want to point out that I am the only representative of the southern hemisphere. So that's something that one should take it into account when we discuss this exercise that usually in this kind of meeting, the southern hemisphere is very few represented. So you have seen this kind of pictures before that asteroid Itokawa has a Boulder distribution that is correlated with the gravitational potential. That, for example, also comet Halley 2 has a correlation between the activity and the chemical composition. Also that there are some so-called activated asteroid that has a very low speed of ejecta. And in fact, I could say that, for my opinion, the so-called main belt comets and activated asteroids are not comets at all, but they are only this kind of Jaken asteroids. But that's a matter of another presentation. So the motivation of this work is that many asteroids are agglomerated bodies maintained by self-gravity, and the impacts produce a seismic wave that propagates to the interior and along the surface at large distance from the impact point. So the questions related to this motivation is, how do these waves affect the entire body? How does the self-gravity influence the propagation of the seismic waves? And then we can characterize the propagation of the seismic wave, for example, to know the wave speed, the attenuation, and the polarization in this dry granular media. So, for example, this is a simple plot of the pressure inside object in an hydrostatic equilibrium, and you see that for a typical 1,000 kilometer or 1 kilometer, 1,000 meter or 10 kilometer objects, you have pressures in the interior of the order 10 to the 3, 10 to the 4, 10 to the 5 pascals. So how does variation in pressure affect the wave propagation? So for that, we have done two kind of things, some laboratory experiments and some numerical experiments. So I will talk first about the the laboratory experiments. What we have done is to build a box, acrylic box, filled with different type of granular media. Then we shoot a projectile, and in order to simulate the self-gravity, we introduce static loading through a hydraulic shack in order to increase the pressure inside the box. The kind of material that we have used is natural material like granite gravel, or artificial glass beads, either these ones, very small ones, or the ones that we have used during our childhood. The kind of projectiles that we use are these usually stainless steel spheres, and at the moment we are concentrating in low speed impacts, so we use this kind of guns that we allow to have something like up to 130 meters per second. And also some free fall. So this is the kind of experiment that we are doing. We record the velocity with the chronogram, the impact with the high-speed camera, and the pressure with the pressure gauge. Inside the box, we have a set of accelerometers and 4 sensors in the walls in order to know the pressure inside the media and the propagation of the wave. And this is the orientation of the accelerometers. Up to now, we have some experiments on gravel and grass beads, and you see here the dependence of the wave speed with the pressure. This is a very flat dependence, and in this case, we see a much steep dependence, and one can compute the relation between the velocity and the pressure and these kind of exponents that we get in one case and in the other. Also, we have some dependence of the wave speed with the projectile speed. So we see that an increment of the wave speed with the projectile speed. And also, we are able to analyze the polarization of of the wave because we have 3-axis accelerometers. So, well, by analysis of the polarization and comparison what we expect from a P wave and S wave, comprehension and tangential wave, we conclude that the P wave is the one that is propagating into the interior, the comprehensional wave. Also, as I said, we have done some numerical experiments. For the numerical experiment, we're using the discrete element methods. The discrete element methods are very suitable for low-speed impacts. They are not suitable for high-speed impacts, as the one mentioned before. For the DEM method, we have used this code, this package, is particles. It's an open source, fully polarized package that implements the DEM method, and it has the advantage that it has several modules for different kind of contact and cohesive force. And well, the visualization, we do it with ParaView. In our case, we have been using generally this model of contact force, or the Hertz and viscoelastic restriction that we are implementing in this paper. One of the experiments that we have done is to reproduce what we have done in the lab. So we have a cubic box filled with on the order of 500,000 spherical particles on the order of 2 to 4 millimeters, and a projectile of 10 millimeters impacting at 200 meters per second. The initial packing is on the order of 68%, so it's quite close to the random packing. And the box is compressed from a sidewall. And here you see an animation of the propagation of the wave into the interior, and well, the color scales with the velocity. So we have important attenuation just a few centimeters from the impact point. The pressure we can measure. I mean, we can measure the pressure with these sensors that we put on the walls. And we can measure the wave velocity through the analysis of the propagation of the displacement of the particles. And we get this relation between the log of the pressure on the walls and the log of the propagation of the wave, the velocity propagation of the wave. And from theoretical calculations, one would expect that in a pure Hertzian model, the velocity should go with 1/6 of the pressure. In our data, it's close to that. If we make a fit of this, we get something like 1/8. And finally, the idea is to put all this information together in analysis of the propagation of a seismic wave into a real object. So what we have done is to develop a new version of ISIS particle that will be released in a few months. We call it ISIS gravity because it includes self-gravity, something that ISIS particle does not include before. We have two implementations, the free body implementation, that's computing the mutual action between all the particles, but this is only possible to run simulation with a few thousand particles. But then we have the many body implementation, that in that case we can simulate up to several 100,000 or even millions particles. And well, this has been tested for some time, and we are pretty happy with the implementation that we have now. This is a simulation of an agglomerated body under self-gravity. In this case, we have something like 90,000 particles of 10 to 50 meters radius, forming a sphere of 1,000 meter radius, so it's a 2-kilometer asteroid. The impact is simulated with a bunch of surface particles moving inward at velocities of on the order of 150 meters per second. So we are not simulating the early stage of the impact. What we are simulating is a later stage where after the initial deformation, we have a velocity field that propagates into the interior. So what we have done is to consider a few particles at these velocities, and they should be comparable to the kinetic energy of the initial hypervelocity impact. Just to give an example, the velocity, the escape velocity at the surface of this object is on the order of 1 meter per second. So everything with red colors should escape from the object. But then we can see that there is a propagation of the wave into the interior and reaching even the antipodes of the object. One of the things that we can calculate is the beta factor that it was already mentioned in the previous talk, as the ratio between the linear momentum at the end of the simulation and the initial ones, and we get values of the beta factor on the order 1 to 3 or 1 to 4, but it depends on the initial linear momentum or the initial kinetic energy. So this beta factor, in our case, increased with the kinetic energy or the initial linear momentum. The linear momentum is computed with particles with velocities less than the escape velocities or particles that are moving inwards into the interior of the objects. So the conclusions are that impacts induced a peak compression wave into the interior. The wave velocity has a dependency with the pressure, but also a dependency, as far as we have seen in our laboratory experiment, with the material. That's something that we have to understand better, what is this big difference between artificial materials like gravel or glass beads. In the simulations, the Hertz and viscoelastic particle has a weak dependency with the pressure, with a exponent of the order of 1.6 or 1.8. And the beta factor depends on the impacting kinetic energy or the linear momentum. For these kilometer-sized bodies, we get a beta in the range of 1.5 to 3.5. The future work is, well, to do some more lab experiments. We have some problem with, in order to get a uniform static loading on the walls. So that's something that we have already solved, but we have not done the experiments yet. And the idea is to extend the experiments up to impact speed of the order of 1 kilometer per second. The numerical experiments, the idea is to explore a range of size for bodies, a wide range of size of bodies, and increase the number of particles, and analyze the outcome of large distance from the impact point. For example, analyze what happens with this low speed ejecta that goes away from the object at distance large from the impact point. And to finalize, we have been working with this experiment of an impact in Japan. And as I said before, we are in the antipode, so I am a little bit aware about the possible antipodal focusing. That's not the case for this small object, but that's something that one has to think about. Okay.
Thank you, Gonzalo. Are there any questions for Gonzalo? Andy?
Yeah, one quick comment. You showed early on the pressure versus radius in the interior of a self-gravitating body. Mm-hmm. And that law is for a fluid body.
Yeah.
Right. In the granular medium, the pressure dependence interior is completely different. I'm sure you realize. This doesn't affect your experiments,
no.
but the people here should know that law is for fluid body, and the granular medium is completely different pressure law.
Now, I show this just as an example because this is, for example, a typical exercise for a planetary science student to compute the
clock.
Yes, I find it gratifying to see in your simulations and also in the previous talk that size distributions of the particles making up the target body are included instead of the same size. On the other hand, I think you should extrapolate that to what is a pretty common condition, which is a marginally catastrophic breakup and reaccumulation in which the largest part of the rubble pile is a substantial fraction, 20, 30, 40% of the mass of the original target, and have the size distribution go down from there.
Yeah. It is possible to use, for this package, it's possible to use a wide range of size distribution. I'm using a narrow range it's also a problem of the velocity of the computation. It's much faster to do it in a narrow range than in a large range.
But then there's fewer particles.
Yeah.
If a lot of the mass is in few big ones.
Okay. Another question, quick? No? Okay. Thank you very much.
I can take it after.
Okay. Okay, so the next speaker is Mike Owen from the Lawrence Livermore National Laboratory. He's the author of the Feral Code. And he's going to talk about these modeling kinetic impactors on a Rubble pile asteroid. So.
Okay, good morning, everybody. So yeah, I'm going to talk about some modeling of Rubble pile dynamics today. And the reason I want to look at this, is because there's a good reason to believe a lot of the objects we may have to mitigate might be Rubble piles, both based on theoretical expectations and now increasing amounts of actual data being returned from missions like Hayabusa, like looking at Itokawa, right? We can see this very rubbly-looking body. And the question we want to answer is, does this structure have consequences for either deflection or disruption that we can measure? A lot of the modeling efforts we've done to date looking at things like kinetic impactors have been on sort of monolithic porous bodies. There have been modeling work done in the past on Rubble pile work as well, and some of that done by Patrick Michel, Eric Asfelg, and others. And so we want to look at the kinetic impactor scenario with this. Now, fortunately for us, the DART mission, which is an upcoming experiment, is a perfect scenario for us to look at because we actually have a chance to compare with reality. Right? So as you've heard several times before now, DART is targeting Didymoon, the secondary in the Didymos system. And it's an opportunity for us to actually verify whatever results we might come up with against the actual reality. I think it's reasonable to think that Didymoon might be a Rubble pile. You know, the idea is like it may be stuff that came off of the primary and reaccumulated. And will this matter in terms of something we can actually measure following the DART impact? And so based on the work of the AIDA working groups, we're going to assume the following kind of properties for Didymoon. That it's like a triaxial ellipsoid, it's roughly 163 meters in diameter, it's got sort of these axial elongations, bulk density about 2.1 grams per cc. We're going to use a granite-like Tilton equation of state to make things simple, which means that has a solid density of about 2.7, and that means to get that bulk density, we're going to assume an average porosity through the whole body of about 20%. And as we mentioned, we're going to use Feral to look at this, which is our mesh-free hydrodynamics code. We're going to use the ASPH model in that, adaptive smooth particles. There's not time to go into all this sort of stuff. We have a lot of equations of state. There's a lot of interesting things in Feral. We've done a lot of verification against laboratory experiments, like this was a gas gun experiment looking at the rupturing of a metal tube due to a plug being fired into it. And actually, right after my talk, Tane Remington is going to talk about some more relevant validation we've done against laboratory experiments as well. Okay, so how are we going to set up these models? We'd like to have some touch with reality. So look, based on photographic surveys from asteroid survey missions, like the Hayabusa one, there's a paper by Mazrui et al. In 2013 where they looked at the this count of boulders, the boulder density you can see on the surface of Itokawa. And they came up with a nice power law with an exponent of minus 3.5 for what that number density looked like. And so I'm going to use that to generate our boulder distribution. There's a lot of free parameters in making the boulders. So the recipe we wound up coming up with is we're going to choose boulder diameters randomly in some radius range. And in the examples I showed today, that range is from 1 to 20 meters in Didymoon. We're going to choose them statistically to match that power law. So we're going to exactly get that power law. Then we're going to take those shapes, starting with just spheres as polyhedra, and we're going to apply random spherical harmonics to each of the boulders in a volume-preserving way to make them blocky and sort of at most mildly non-convex. And then we also decided that we would like to have some tendency of size with depth. And there's various ways to do that. You can argue about your favorite model. What we actually decided to do was make them so you would tend to have the larger boulders deeper in the object. So we sort them inversely by size, and then put them in the body randomly, somewhere where they don't hit anything that's already there, and let them be repelled by the surface until they encounter something and settle. And you do that sequentially and build up the structure. So if you do all that, this is an example of what we get. And I'm going to show 2D and 3D examples here. So here's my Didymune ellipsoidal shape. Here's the 2D ellipsoidal shape, and this is the 3D. I'm going to fill these things. In this case, I filled the 2D shape to about a 75% fill factor of boulders, so there's 25% volume left for something else, which I'll fill in with some matrix material. You can see the zoom in here of what these boulder shapes kind of look like, and like I said, they tend to be kind of blocky. They're maybe not as elongated as they should be, but it's a good first step. And you can also see this tendency with depth I was just talking about, where most of your bigger things tend to be deeper, and you have smaller objects near the surface. Okay, and so and the same thing in 3D occurs. So this is our 3D surface as a polyhedron, and you can see all the polyhedra inside here, which are our boulders. And some of them poke through the surface, and I allow them to poke through the surface, so we have kind of a rubbly surface going on here. That's actually a choice you can make, and I thought it was more realistic to have them actually protruding. Okay, so then, and so in the 2D case with the 75% fill, we have about 1,900 boulders in this shape. In 3D, we have about 23,000 boulders. And then once I have these polyhedra, I can use various algorithms to fill them with the ASPH points. And so this is colored by material type, those point distributions. And so you can see the black points are the boulder materials, and every individual boulder is filled in with boulder material. And the purple points are the matrix. And I'm going to have different properties for those two things. So my choice in this case, they're both going to be the stony, same kind of granite-like equation of state, but they're going to have different porosities. Okay, before I get into this, I should mention, so on the left here, this is a zoom in of a 2D model of the impact, and on the right, the same thing with the boulders. So this is the monolith case for comparison. This is the boulders. These both have the same bulk density of 20%, so that's the whole story for the monolith. In the case of the boulders, I decided to give the boulders less porosity, so they're 0.1. It's an arbitrary choice. And that means to balance out the overall porosity, you have one up with 50% porosity in the matrix, so it's much fluffier. And then if you start this up, hopefully, yep. In these two cases, so our impactor came down, hit, makes our crater in each case. The craters are roughly similar in terms of size and so forth. Their morphology is a little different because this one happened to hit right on a boulder here. What you're seeing here is the purple and the red are the material, and as damage accrues, you see this blue scale occur, which is the amount of damage, shading from dark blue to white. And so you can see this boulder, which was right near the impact site's been destroyed, and a lot of the matrix around there, and that's the kind of material that's flying off as this thing goes on. Okay, so what does all that mean actually in terms of what we'd measure, like for instance beta, which is something we care about a lot. So if you look at the on your side, the left plot here, this is 7 different realizations of the same object, okay? So they all have the same 20% total porosity. The dark black line here is the monolith case of beta, and it comes in at about 2.5 over time. And then I have 6 different realizations of the boulder field. Now remember, I created the boulders statistically. So if I could just spin the random number generator, I can make different realizations of the boulder field. Other than that, everything else is the same. So all the bulk properties of these asteroids are the same. They have the same porosities and so forth. And I'm actually getting a spread of about a factor of 2 between the min and max beta just based on changing the geometry, spinning around where those boulders are. This goes to a question we had a little bit ago about sort of the variation you might see in some of these things. And then you can actually break that down. And so this plot on the right is basically the same information. It's the same 7 simulations, but I've also plotted the contributions to beta from the matrix material, that light interstitial material, and the boulder material. And for this 2D model, the majority of your beta tends to come from the boulder points, although there are some cases where the matrix is almost equivalent. So there's a lot of randomness in this. And I should also always get the caveat with this, 2D results are notional. These numbers aren't to be trusted until we actually have the full 3D story. Okay, so what's going on here? Why do we have this variation in beta? And so what I'm showing here now, this is the impact site for 3 representative cases. So this is a low beta case, sort of an average beta case. So this one looks a lot like the monolith result. And this is a high beta case. And so there's our impactor. It's going to come down vertically. So let's start this off and see what happens here. If we can get those going. Yep. Okay, so look what happened now. So in the low beta case, our impactor came down and encountered a fairly oblique surface on a boulder that happened to be in the way. And when it did that, the ejecta comes off more to the side, and then immediately encounters another obstacle here, another big boulder that happens to be downrange of where that debris is coming up. And so that entanglement of the material and the ejecta coming off makes it much more complicated, and you tend not to get as much material being thrown up. And that's sort of why this one's being suppressed. There's two effects. There's the oblique impact, which we know from other studies can affect beta. And there's also this Pacheco machine effect of encountering downrange stuff on the surface. The average case, let's go to the high beta case. So the high beta case, we came down, happened to encounter, we were lucky. We hit a boulder on a flat surface pointing up. And in fact, it was almost submerged. The flat surface was just touching the surface. And remember, that boulder was 10% porosity, even though the overall porosity of the whole object is 20%. Well, that boulder took the brunt of our damage there. And so it behaved like a less porous object, effectively. And we got a little more beta push out of that from destroying that boulder. And, and that ejecta didn't have a lot of trouble encountering other stuff. And then the average case kind of splits the difference. You know, this was a little bit oblique. It hit near a boulder again. It was a little oblique, not too oblique, and it didn't have that much entanglement with the ejecta. And it kind of averaged out. We got close to the monolith case for that result. Okay. Something else I should mention all this that I found very interesting is that the damage propagation internal to the structure is different when you have the monolith versus the rubble pile. If you remember when it showed that monolith result, you tend to have a devastated region and then big macroscopic fracture planes coming out of that crater. The rubble piles are a little different. They tend to shake around these dense boulders. If you remember Angela's presentation, you can see the pressure waves bouncing around inside the boulders because signal wave speeds are higher in there. And then that causes the matrix material to be damaged around them. And so you tend to get fractures propagating in the matrix material around the boulders. So there's actually a difference in the interior propagation of the damage, but I don't think you'd necessarily see a result from that in a deflection experiment like DART. It might have consequences for disruption, though. Okay, so again, 2D only is instructional. We actually need 3D to really get real numbers out of this stuff. And so we are pursuing the 3D now. So this, again, is going to be a comparison of a monolith case versus a rubble pile. Get these two going. Okay, so we have our impact site, and you can see our ejecta cone coming out of each of these cases. And once again, we have this sort of macroscopic fracturing pattern coming out of the monolith. And a kind of a different pattern occurring over here in the rubble pile, where it tends to propagate around to come off the boulders. In terms of beta, the time evolution of beta is a little different than the 2D case. So far in our 3D model, in fact, the matrix material is dominating beta. Now, that case I was looking at, it struck directly in the matrix. Remember, the 3D actually was 50% matrix, so it's more likely to hit there. There could be a 3D effect here as well. We actually need to evolve these things further in time to really get the final answer, so this is still a work in progress on the 3D results. Okay, just about on time. So our initial results, we think, are pretty interesting. We can generate a variety of interesting rubble pile structures for use in modeling things like this. It's very easy to do now. We're just filling simple ellipsoidal shapes in the examples I show here, but we can actually fill any polyhedral shape. The 2D results are well in hand. They show some interesting trends. The two things I think are interesting is that just varying the boulder realization can vary beta based on where you hit, because kinetic impactors are very local. They sample what you hit right in that area. Craters are a little bit different. The damage propagation internal to the body is quite different, and that may have implications for disruption. And bear in mind, again, 2D is instructional. So we've shown some preliminary 3D results, and we're still working on those right now. And with that, I'll take questions.
Thank you very much. Are there questions for Mike? I got one. Okay. Why don't you include voids also in your rubble pile?
You could put voids in. So we could choose not to put in that material. And in fact,
it would be interesting because in our, concept rubble piles contains also macroscopic voids, and of course the shock wave will reflect. So it would be an interesting case to look at.
So my thinking is the matrix material in this case sort of represents the unresolved low end of the size distribution.
Yeah.
But we should actually test varying that minimum boulder size with our matrix and see if we reproduce the behavior we want when we do that. And there could also be ice or something else in there. It may actually be a different material,
Yeah.
which would be interesting.
But void would be interesting.
Yeah, void's interesting, yeah.
And, okay, no, I'm not of you. Thank you very much. If there are no other questions, because time is running. One quick, okay.
Did you change the impedance properties between the matrix and the block, or were they all basically the same impedance? So you're just looking at porosity differences in your
So
calculation?
it's a porosity difference only. Now, in the implementation we have, that affects.
So did you change the impedance between the matrix and the border? So the sound speed, basically.
Yeah. And so the sound speed in this model is affected by the porosity. The porosity is quite different. And that's why the wave speeds were faster. in
Okay,
the
but you
solid
didn't
voltage.
change the material properties at all,
No.
in other, besides the porosity?
No,
Okay.
besides the porosity, no.
But
Although
that might also be different, actually, between the matrix and the blocks to some extent.
Yeah.
So,
Yeah, once we have a heterogeneous body like this, there's a lot of parameters we can vary. And I think making a different material for the matrix would be an interesting thing.
Okay, Andy, quickly.
So if you could image the surface before the impact and after the impact, would you be able to tell the interior structure based on the crater size and morphology around it?
So the crater morphology was a bit different, but it was subtle. I think we need to actually do the statistics to see if we can really see that signal. And so we need that 3D result really to answer this as well, but maybe.
Well, I think, I mean, as we saw, it really depends on what is locally. If you hit a boulder versus a matrix. So if you hit a boulder, you won't know that is a matrix below, right?
Right.
So I don't think it's obvious. Anyway, okay, interesting. Thank you very much. Okay, the last talk is by Tane Remington from Lawrence Livermore also, and that will be benchmarking asteroid deflection experiments.
Good morning, everyone. Thank you, Patrick, for the introduction. Again, my name is Tane Remington, and today I will be presenting on benchmarking asteroid deflection experiments. I am part of the Planetary Defense Group at the Lawrence Livermore National Lab, along with Megan and Mike, who you've already heard from, as well as Suhail, who will be speaking tomorrow morning. And as Mike just explained, we try to, as a group, understand how to deflect potentially hazardous asteroids that may impact Earth. Specifically, we try and understand how to deflect these asteroids, monolithic or rubble pile like Itokawa, using kinetic impactors using our simulations, which begs the question, how do we know our simulations are correct? So we validate our code by benchmarking hypervelocity impact experiments to ensure that our simulations accurately demonstrate how to deflect these asteroids using a kinetic impactor. You've already seen this slide by Megan and Mike. Just to reiterate, the code that I'm validating is Spheral, an adaptive smooth particle hydrodynamics code. In all my simulations I'll be showing you today, I have used the Tillotson equation of state, the tensor generalization of the Benz-Asphalt damage model, and in most of my simulations, unless otherwise stated, I have used the pressure-dependent Collins strength model for rocks. Today, I will be focusing on the benchmarking of the 1991 gas gun experiment conducted at Kyoto University by Nakamura and Fujiwara, where they shot spherical basalt targets with spherical nylon impactors, where these impactors were nominally around 1/10 the size of the basalt targets. These nylon impactors hit the basalt targets at an angle incident to the surface of 60 degrees, and were traveling around 3 kilometers per second. So here I have a video that was done in Spheral showing this nylon impactor and the basalt target, and you can kind of see the scaling there, since there was no pictures in the publications. And let's see if this works. Upon impact, you can see the fragments flying off in different directions. giving a very good physical representation of what the experiments showed. In this photograph here, you can see this was taken with a high-speed camera. So we want to compare these fragment masses and velocities in spheral here to the experimental results, while also taking the opportunity to investigate the sensitivities of our simulation results to material parameters, strain models, strength models that you can select in spheral. We find that the strain model selected affects the damage morphology in our target material. You can select two different strain modes in spheral. One is the Benz-Asphog strain mode, and the other is the pseudoplastic strain mode. The Benz-Asphog strain mode is your typical strain model used in SPH codes where you follow deviatoric stress with regards to pressure. The pseudoplastic strain mode was added as a new feature to our ASPH code where the deviatoric stress is followed without the absolute bounding of plasticity. When we use the Benz-Asphog strain mode, we find that through the reflections at the back of the sphere, we get a spall plane created, and you can get this characteristic spall wall where you get fragmentation on the outer surface of the sphere and a preserved inner core, which is shown in blue. So up here, I have the entire sphere shown here during impact, and down here is a slice through the Z-plane so you can see the cross-section into the sphere. And the colors are the effective tensor damage trace. So when you compare this to the experimental results, you can see in this photograph here this characteristic spall wall where you have large fragmentation and a large preserved inner core, matching what we found in spheral when we used the Benz-Asphog strain mode. When we use the pseudoplastic strain mode, instead what we find when we're looking inside the sphere itself here in this cross-section, you can see damage has propagated throughout the entire sphere, leaving no large remaining target fragment mass, morphologically not matching what was found experimentally. To investigate the sensitivity of the spheral results to the selected material parameters, we look at the size of the largest remaining fragment that depends on the power law distribution of flaws. Since no material is ideal, all materials have inherent flaws, we need to add this characteristic into our target material in spheral. To do this, we employ the two-parameter Rubble methodology to see the experimentally determined statistical distribution of flaws into our target material, where K and M are material parameters that are determined experimentally for a specific material. So simply put, by using this two-parameter Rubble methodology, spheral is implementing flaw distributions into our basalt target material to better represent what we would realistically find in a basaltic rock. In 1991, when this gas gun experiment was being conducted, Nakamura and Fujiwara did not actually measure the K and M parameters for the Yakuno basalt used as the target material. So other groups with SPH codes that wanted to use this gas gun experiment to validate their own codes were subjected to doing arbitrary K and M parameter scans to find simulation results that best match the experimental results. So Benz and Asphog did this for their own SPH code, where they found the exponent M parameter equal to 8.5 to best match the experimental results for larger fragment masses, but not so much for the smaller fragment masses, where the experimental results are shown in these red circles and Benz and Asphog are these yellow squares. When we used the exponent M equal 8.5 in spheral, we found plane to look at this cross-section, and we were able to find the largest remaining fragment, that's this core here, which actually looks very much like the experiment itself. It's a very good match. In any case, after Benz and Asphog had done this scan and found M equals 8.5 to be the best parameter match, Nakamura went back and measured the K and M parameters for the Yakuno basalt used in this specific gas gun experiment, where she found the exponent M to equal 17.2, which could mean very big differences in our simulation results since M is an exponent. When we put M equals 17.2 into spheral, we found that we're actually able to match the smaller fragment masses much better to the experimental trend line, but not so much the larger fragment masses, where 17.2 are the blue triangles. looking at the morphology and cutting into it and finding the largest remaining fragment masses, you can see there's 2 large remaining fragment masses, but not 1 single remaining core. However, this is not as alarming as it may seem. Simply by varying the random seeding of flaws in your target material, you would change the largest remaining target fragment mass and match the experimental findings within some error bounds. But the distribution of the smaller fragment masses is expected to stay the same. So we're pleased to find that our spheral results match the experimental trend using the experimentally measured K and M parameters by Nakamura, and did a better job than the arbitrarily measured and widely used parameter m equals 8.5, meaning spheral is sensitive to the material parameter selected, as it should be, as we had hoped, and can do a really good job physically representing what is observed experimentally when given really well-analyzed initial conditions. We compared the fragment velocities in spheral using m equals 17.2 and 8.5 to the experimental results and to the results by Benson Asfog for parameter m equals 8.5. And what we find for our spheral results shown in blue and black is that there's a girth of fragment velocities for the smaller fragment masses, sandwiching the experimental trend line shown in red. The results by Benson Asfog underestimate the experimental trend line, and they also used an M parameter of 8.5, so we found it interesting that our results in spheral for using a parameter of M equals 8.5 didn't match what Benson Asfog were finding. Instead, we see that the spheral results for 8.5 shown in black have a concentration of smaller fragment masses for this fragment velocity range. And for M equals 17.2 in spheral, we find that it matches the results for M equals 8.5 fairly similarly, and we get this curious gap in fragment velocity for the smaller fragment masses. So we wanted to investigate why we're seeing almost 2 trend lines in our spheral results. So we probed the strength models and found that the strength models do affect our simulation results. When using the pressure-dependent column strength model, we find that we get this broad range of velocities for our smaller fragment masses, but when we use the constant strength model, where the shear modulus and yield strength are fixed, this broad range of fragment velocity shrinks to become 1 trend line, matching the experimental trend line shown in red almost exactly. We didn't want to just stop here. We know that a lot of things are dependent on each other, and I wanted to investigate if I changed the shear strength at 0 pressure, if I did a scan for this, would that change this range of velocities we saw here? And for the next slide where I did a scan, I'm just going to tell you, no, it didn't change that range of velocities, but it did show very interesting damage morphology within the spheres. For a low shear strength at 66 megapascal, you can see that damage propagates throughout the entire sphere, where again, the colors are the effective tensor damage trace, and we're looking into the cross-section of the sphere. When I increase it to 130, you can see this characteristic spall wall and a little bit of a preserved inner core, but not so much, and over time, eventually, the whole sphere fragments. It's only at 600 MPa that you start getting a large enough core to match the experimental results fairly well, and the same can be said for the constant strength model. So in summary, we are encouraged by our current results, which indicate a number of sensitivities. We find through the scans we've done so far that we have learned that the simulations are able to produce similar damage morphologies to the experiments. Damage morphology is sensitive to the strain model used. Damage is sensitive to the distribution of flaws in the target material. Fragment velocity distribution is sensitive to the strength model, and target material property selected in the pressure-dependent strength model changes the damage morphology in the target. So we continue to build upon the work presented here, while also benchmarking other hypervelocity impact experiments. And with that, I thank you for your time.
Thank you. Thank you very much. Are there questions? Who? Yeah, Siegfried.
Thank you. A very nice talk, and it's actually more of a comment than a question. So what I particularly like about those presentations is that you try to validate your codes with experimental data. And with kinetic impact, that's kind of possible. So my concern is that with nuclear deflection methodologies, and that also plays into the discussion yesterday, I would like to see those graphs too. Probably they are ITAR, right? But there should be something like that, because as you've shown very nicely, if you don't adapt your model to physical data, you may get some results that are completely off, right?
Yeah, so we don't try and adapt our model per se. We try to refine or make enhancements where we see fit. And I think the important part is that you have to start somewhere, and since the kinetic impactor technique is the most mature out of the techniques available, we start our efforts there. So of course, I definitely agree that validating the code by using experimental results is very important.
Ellen?
Yeah, I just wanted to reiterate that's just a really wonderful benchmarking study that you've done, very, very comprehensive. And I was interesting to see that the Benz and Aspog strain model produced the core type fragmentation and hypervelocity impacts. And I wonder if you can do further benchmarking tests to see if you reduce the impact velocity below the hypervelocity limit, below 1 kilometer per second. What we see in the laboratory is not a core type fragmentation, but more orange sectors type fragmentation. I wonder if that strain model could be tested further by, like, say, a 300 meter per second impact velocity, and if it reproduces that damaged morphology.
Yeah, so I'm actually doing benchmarking of Benz and Aspog, Hausen and Holzapfel experiments, and looking into the lower velocity range, I think between 700 meters per second and maybe over a kilometer per second. And there's some very interesting results there, so I'm happy to talk to you about it afterwards. I can show you actually some of my results.
That sounds excellent. That's a really, really neat addition.
Thank you.
Okay, thank you. I have one comment and then an announcement.
Sure.
For the M equals 17, I was co-author of this paper, and I don't think this is the right value for this. The reason is that the M equals 17 was measured almost quasi-statically, while so very low strain rate, while these impacts are very high strain rates, so you reach the smaller cracks, and the M parameter actually changes as a function of the size of the cracks. So in particular, the largest cracks have a steep slope, so large M, and the small cracks have a lower M. So I would think that for this kind of experiment, M equals 17 is a little too large. But we can discuss it afterwards.
Sure, we can discuss it later, yeah. Thank you.
I have an announcement before we stop, and actually it's related to Nakamura. Next year, there is the organization exactly in 1 year of the 9th Catastrophic Disruption Workshop. So this is a workshop that we organize every 5 years. The last one was in Hawaii in 2013. It was also my honeymoon, so a workshop called Catastrophic Disruption was not really promising for a honeymoon. So the next one will be in Kobe, exactly in 1 year, and this is a 3-day workshop for the disruption community, not disrupted community. So, thank you.
Yeah, one short final remark before we have a coffee break. I have more speaker release forms here. So I put them just down here in front here of this stand. And if you need one, grab it and please then return it to the registration desk.